everyone, and welcome back to the second half of day one of the Smart Lab Exchange for R&D. I hope you had some insightful discussions during the roundtables and your business meetings. And it's my great pleasure now to introduce to you the two speakers for our next presentation by Mestrolab. So I welcome Guy Desmarquet. He's Senior Vice President, Global Sales and Strategic Partnerships for Mestrolab France. Guy received his PhD in molecular biology from Lyon University. He was responsible for driving sales at ACD Labs for nearly 2 decades. Guy is in charge of the worldwide sales organization and is also leading the third parties relationships at Mestrolab, supervising more specifically the strategic collaboration with Bruker, as well as leading some informatics areas of the company, such as, among others, automated knowledge generation from analytical instruments or data standardization. Second speaker, and I already see him here in his video. Hello, Gary Sharman.
Hello, hi.
Gary is the Senior Scientific Director at Mestrolab UK, and he joined Mestrolab after more than 20 years working in the pharma industry, more recently for Eli Lilly, where he spent 15 years in discovery chemistry at the Earl Wood site in the UK. He worked within the analytical chemistry group, specializing in NMR spectroscopy and the processing and management of data. Prior to that, he worked in the NMR group at AstraZeneca, within the development chemistry group at Macclesfield, UK. Guy and Gary, we are looking forward to your presentation. The stage is yours.
Great, thank you. Does everyone do you hear me nice and clearly?
Yeah.
Great. So I just share my screen, is that correct?
That's correct.
Great. Just Gary, we're having some, I don't know if you've seen my message in chat, we're having some issues bringing Guy up, so hopefully we'll have him with you soon, but if you can get started, that'd be great.
That's okay. Yeah, that's fine, because I was actually going to deliver the bulk of the talk anyway, so we can make a start to keep things on schedule.
Fantastic, thank you.
Does everyone see my screen okay?
Yep.
Okay, great, thank you. So thank you very much for the introduction. What we're going to talk a little bit about today is the journey, I guess, we've come on as a company with the automation of processes and how commonalities kind of came out to us as we went along that path, and how I guess we also learned to deal with the specifics of those processes as well. Okay, so just to give you a bit of an overview to the talk, we're going to start off with something telling you a little bit about the history of where we got to where we are. We'll then say a little bit about how we thought about the problem in a more abstract way, and our philosophy, if you like, of dealing with automation. And then our solution to that, the way we've come up with of dealing with automation problems. We'll have a few examples of how we've done that, and then perhaps talk a little bit about how we can make connections to other systems which are very necessary for truly integrated automations. So going back to the kind of origins of the company, we started as an NMR processing company. We later expanded to other techniques, LCMS, UV, IR, and so on. And I guess inevitably, as more people use the software and they solved problems with the software and used it to report and generate useful information, their thoughts turned to automation. So, you know, now I've got so many of these samples, I need to be able to automate the process for dealing with them. And so many times customers would come to us and they would ask about help with automating their process. How can we use your software to automate this analysis or this other analysis? And I guess as they did that, we found that certain requests kept getting repeated. And I think the developers started to get kind of almost sick of hearing the same requests again and again. So, you know, for example, although the automation processes we were being asked about were very different, there were lots of things they kept getting asked. For example, I need to find my data in a folder, or I need to listen for new data that's appearing on an instrument and then operate on it as soon as it appears. Or I need to have a report and it needs to be in a very specific format that I need it to look like to send back to my requesters. And so as these things happened, I guess they started to step back and maybe try to think a little more about how they could make the process more generic and how they could reuse things rather than keep developing the same thing over and over again. Okay, so in doing that, I guess what we thought is that, from our point of view at least, there were a number of common steps that pretty much anything we got asked to automate featured. And they're really the 5 things that you see here. So a process would typically start with finding data and perhaps associating it, so the right data end up being processed with the right data. Somehow doing some preparation on that data for NMR. That could be extracting multiplets, for example, or maybe it's integration of a chromatogram or something like that. And then once you've got that done, there's a kind of a core analysis part. And this is maybe the bit that is specific to an individual workflow, where you do whatever it is you need to do for that particular process. But once you've done that, typically people would want to make some kind of report that they could share with their users. And then finally, they would want to save the results. Now that could mean the report file, it could mean saving it to another system, just a result, just a number, even something that was abstracted from that process. Could be saving it to a database, but some kind of saving of the results at the end of the process. And I guess what they found is that this was more or less the same pattern, whatever we were asked to do in terms of automating a process. Now, there's perhaps one other very important element to that, and that is interactions with other systems. We're not operating our automation in a vacuum, and typically data may be gathered from other systems or even pushed from other systems at the beginning, and typically you may need to save data at the end into some external system as well. So the ability to interact outside of the engine that we've created was also seen as being very important. So a couple of other sort of general things that they kind of thought about as these requests kept coming in for automation, and that is that there's perhaps a useful distinction to be made between automating a sample or a test and extending that automation to a whole batch. Because very typically what would happen, if I perhaps just try and show my pointer here, is that automating a sample would involve taking some data and making some kind of report from it. But more often than not, automating a batch just means doing the same thing lots of times. So what that kind of means is there are certain parts of the process that relate to a sample and other parts that relate to the batch. And you can kind of almost separate those two things out more often than not. So what does that mean in terms of those 5 boxes that we had before? Well, perhaps we can kind of think about it like this. If we think about the automation of a sample, so taking a set of data and generating the report, it's really the last 4 of those boxes that relate to that. So preparing the data, the core analysis, making the report and saving the results. So that thing we may repeat lots and lots of times, but we're doing it on the basis each time on the basis of a particular sample. And of course, that may be more than one piece of data, but it's one document, if you like, within our world that we're talking about here. On the other hand, if we think about the batch automation, really it's about finding the data to then push into the rest of the process, which just allows you to do the same thing lots and lots of times. So finding it could be listening to an instrument, it could be searching a directory or a database, it could be taking some kind of mapping file or another input, perhaps from a web service or call or something like that. And then typically there's also a step there to kind of organize that data as well. Once you've found it, which bits are supposed to go with which. In the NMR world, for example, perhaps a proton and a carbon spectrum need to go into one analysis, and you need to make sure that the right one goes with the right one. Okay, so I think we thought a little bit about how that process can be generalized. And as I say, that really came out of stepping back from being asked the same thing lots of times. So being asked again and again to do similar things led us to step back and try and conceptualize it a little bit more. But there are probably a few other things as well, just to summarize this kind of general features that we see. And that is that there are certain other things we would often get asked. And that would be that the points that you see here. So, for example, it would have to be something that was easy to set up by a non-expert. If you wanted to find a list of samples, for example, ideally the expert in the technique needs to be able to do that, but it shouldn't need an IT expert to be able to do it. So we wanted to make that as simple as possible so that the end user, if you like, could create these workflows in the first place. I guess another important part of that is creating reports that look the way you want and not the way the software wants them to be, because very often users would have a very specific idea about what needs to go in that report, what it wants to look like, how it should be formatted, and so we need to make sure that we can support that. And yeah, I guess the final thing is that all of that should take either no code at all, so just pure configuration, or the very minimum amount of code for the most difficult kind of integrations to be done as part of this process. The process should be very transferable. So once a technique expert has created it, they should be able to give it to a non-expert to be able to run it, or maybe to hand on to an IT colleague to deploy in a larger installation. And I guess, yes, the last 2 points really speak to that as well, that I guess that the scientist in the lab maybe doesn't want to have to keep pestering their colleague in IT every time they want to make a little change to their process. They want to be able to do that themselves where it's allowed, at least, and it's not locked down by GXP, which obviously we can allow for as well. So we don't want that overhead, if you like, to be passed on to the IT group. And I guess as a part of that too, we need to make it scalable in such a way that workflows don't need rewriting when they're scaled up to the next level. We can keep reusing the same things that we've already created, and we can allow those integrations as well with either laboratory informatics systems or other third parties. So these are all of the thoughts we had, if you like. As I say, they came from people using our software and asking for automation, and it had kind of led us to try and create something that would meet all of these different thoughts that you've seen here. So our solution that we came up with, we called MGears, and I'm going to tell you a little bit about that in the next few slides. So the way it kind of works, I like to think of it as sort of 3 layers, if you like, and the innermost layer are what we call plugins. or bricks, and they deal with a specific task. So remember when we talked about our general workflow, we said that there was always a specific thing that was the particular analysis in hand. And so we have a plugin or a brick that deals with each of those. So it could be verification of a spectrum against a structure. It could be determining the concentration of something perhaps automatically, or a purity, but we can have a specific plugin that deals with that particular analysis. Then beyond that, you have a kind of layer around it that deals with the sample automation. We call that MGears, but it's really what I described as sample automation before, where we take one or more sets of data and we turn it into report. So we're doing all of the other bits of that sample automation there. So we're doing any pre-processing of the data, we're applying the bricks, but then we're formatting the report, saving the results, and so on. And that's done from within the automation engine. And then finally, we have this kind of outer layer of full gears. And what that's doing is it's taking those sample automations and it's repeating them lots of times on the data that it's either found or been told to process. And so that enables you to now run batches of samples using the same automation that you've done for single samples. So what does it actually look like in terms of setting it up? Well, I guess the design very much follows the steps of automation that I spoke about a little earlier. So we have a number of tabs within the software that deal with that. An input tab that specifies where the data is found, how it's grouped together, and so on. Pre-processing, plugins. You can probably see the parallels here with all of the 5 areas that I described before. The reporting is the design part, and then the output is the saving. And actually what you see here is a list of some of those bricks, those advanced plugins that can do the detailed tasks within the workflow. But all of the setup of this is configuration. So it's clicking boxes, selecting options, and so on. And the majority of automation tasks you can deal with in that way. So one of our aims was to have no code. And so you can do that. You can automate a task completely with no code and just configuration. But then I think we did say that that may have to be low code. So we always provide hooks as well to do custom things for individual processes. So maybe, for example, you want to go and retrieve a structure from your corporate database. Our script engine allows you to do that and plug that into the process. So again, just to reiterate that, I guess the whole idea behind this then is that you can create and optimize workflows, but you don't need us to do it for you. So you don't need professional services. You don't need, for the most part, custom programming. A technique expert can go in and create a workflow that's scalable and that they can use on large numbers of samples. So we've just got a few examples of some of the things that we can do that we've deployed in fairly large scale. Now, these are just examples. There are lots of other things we could have talked about today. We just picked a few to discuss for the talk. So the first one of those is verification. So I guess this is a fairly common automation task with spectroscopic data, where maybe what you have are some a candidate structure, candidate chemical structure. You have some data, perhaps NMR data or perhaps LCMS data. And what you want to do is automatically determine whether that structure is consistent with the data. So we can set up a workflow to do this. We can use one of our custom bricks for verification to do the business end of the work that's actually going to score the data and assign the structure and so on, as you see here. But the wrapper around it will allow this to be done many, many times and produce a nice formatted report, and to slot into other processes within the company. And we have this kind of workflow deployed in several large installations. Actually, one other thing it might be worth mentioning here as well is, as well as doing the verification, I think this particular workflow also looks at the quality of the data itself, because I guess one reason for failure could be kind of rubbish in, rubbish out. If you don't feed it good data, that could lead to a failure. So it kind of tells you that as well, whether the data is good enough for the analysis. Another application which we've worked with some partners and deployed is something we call best method. So here, this is something that enables perhaps a purification service where impure molecules are submitted into that service, and what the submitter wants back is a POPs with a pure compound in it. And typically what might happen is that they would run a number of scout experiments with different chromatographic methods, and they would look for the target within all of those methods and look for the method that best separated the target from all of the other rubbish that's in there that they don't really want. So typically that means looking that the peak is clear of the other peaks, it's well resolved, but also that the peak itself is pure and shows no signs of anything else hiding underneath there that would ruin the chances of purification. So we can do this automatically on batches of samples. So again, as you see in the kind of picture here, for sample 1, we might have 3 different pieces of data. We need to evaluate them together, score them down to a very simple score, which is just a number between 0 and 1, telling you how good the method is. And from that, you can make some decision about if it's good enough or if you need to do more work on method development. And then again, that gets repeated for sample 2, and so on and so on. So this is another process that we've automated using the MGears platform. And then one final example, actually also related to LCMS in this case, also shows the ability to kind of do review. That review could be by exception if you want. And this is a reaction optimization example. So the idea here would be that a chemist is trying to find the best conditions for a reaction. They perhaps do the same reaction many times, varying things like solvent or catalyst or temperature and things like this. And they're looking for the conditions that give the most product or the least starting material or the least byproduct and so on. So the MGears workflow allows you to define the things you're interested in. It then processes a whole set of LCMS data and gives you a kind of nice overview of which ones are best, which ones are worst, and so on, from which you can make data-driven decisions about what is the best way to do things. So a couple of other things, we can make formatted reports. I mentioned that before. And we can also create these kind of decision-making dashboards within a database if necessary as well to help along with those processes. For the final few slides, though, what I'd like to do is just talk a bit about integration with other systems and an example of that. So one of the nice things about the Gears platform is that it's very scalable. So it means that a user can develop a workflow on a single sample, and they can run it within a graphical user interface. They can then use the same workflow to expand it to a batch. And here you just see a kind of log file from the batch running many, many samples. And then they can even deploy that workflow when you're happy enough in a kind of headerless environment, in the cloud possibly, and run that on very large numbers of sample when you're happy that it's reliable and you're happy to let it rip on data in that kind of way. Another thought here, I just realized there's a build on this slide, so I will skip forward to see all the things there. Another kind of thought is that as I said before, we don't sit in an island, and we don't live on an island. We know that the automation exists within a much wider, a much bigger picture. There are layers of instrumentation, there are laboratory informatics systems to interface with. So it's very important that we interface with with those effectively. So the automation engine can do that through a number of mechanisms. We can exploit the sort of underlying scripting engine to have it go out and look for information or send information out, perhaps either via a call to a web service, a REST web service, a database or file system. We can send it orders directly, either on the command line or by dropping in simple JSON files that describe what work it needs to do, and then it will go away and do them. Or we can actually wrap it with something we call MNOVA server to expose those functions in a fairly standard way, so other things can come in and call it by REST. And I think you see a kind of picture of that here as well, where we have a sort of very standard interface, probably many are familiar with, to go in and see those things. So just for the very final couple of minutes, what I'd like to do is mention a project that does show this kind of integration. So this is this Future Lab project. So I should mention here some funding this has received from the European Union and from the governance of Galicia. And in particular, what we're talking about is this quantitative NMR workflow. And the way it works is this. We have a web-based submission where a user requests a quantitative NMR, a purity analysis. That analysis request is sent to the NMR. At this point, you still have to take the sample there. We haven't managed to automate the matter transference of the sample yet, so we need to put the sample on there. The NMR is run, and then that MGears process, the same engine we've been discussing for a while now, runs the analysis and sends the results back to the user. So it's integrated in this much wider end-to-end system. And what you end up with from that analysis is a report that looks something like this. So we've, in this case, an NMR spectrum. It's done all of the necessary calculations. It's calculated the purity. This can be done in a GMP compliant way. And then those results are reported back to the requester in a completely automated way using the underlying automation engine that we've been discussing throughout this talk. So just to finish up then, I think we've seen from this journey with automation that there are many common things in the automation process, and we've tried to make those reproducible and reusable so that we're not reinventing the wheel every time we have to do them. But at the same time, we need to allow for the specifics of an analysis or specifics of connections to other systems. And that I hope we've illustrated here as well with some of those examples. And hopefully we've got something that brings these things together to enable these kind of automations. So just a final slide to say thank you, particularly to the Mesh Lab development team and Augustin in particular. I'd like to single him out. And thank you to you for your attention.
Great. Wonderful. Thank you so much, Gary. I think we have time for one question. Are there any questions or comments from the audience? If not, then I have a question. Your talk will be followed by presentations from some standardization initiatives. How do you deal with data standards in your software?
So we can export to standard formats. For example, allotrope is one of the ones that we can do. And Guy, please feel free to add more here as well. So we can put our results into along with the raw data into that sort of standard data package. So that would be typically the way we would do that. I guess we could also, obviously those abstracted results as well, those data reduced results can be stored into whatever system we want. But yeah, I mean, you could even imagine an automation process in itself that's only purpose was to generate the standardized data, right? That it may not be doing any of this fancy analysis. It might just be taking raw data and exporting it in a standard format. And in fact, that's one of the workflows that you can do from within here.
Okay, great. Thank you so much. Again, this was really interesting. Let me now introduce the speaker of the next session, Corey Bakalarski. He is the vice chair at the Allotrope Foundation in the USA. Corey is a principal bioinformatics scientist at Genentech, who leads the computational proteomics and analytic data science group with over 20 years of experience marrying the life sciences with computational technology. Currently, he is the vice chairman of the Allotrope Foundation, and Corey holds a doctorate in cellular and developmental biology from Harvard Medical School. Corey, it's a pleasure to have you, and the stage is yours. You're on mute.
You need to unmute yourself there. Thank you.
Great. Thanks, everyone. Let me see if I can share my presentation.
Yeah, we can see it.
Perfect. Great. Well, thank you, everyone, and thanks, Annette, for the invitation to come and speak today. So I want to tell you a little bit about what we've been doing with Allotrope, and I'm sure a lot of you are familiar with Allotrope and a lot of the standardization initiatives. So as was just said, my name is Corey Bakalarski. The day job, so to speak, is a principal bioinformatics scientist with Genentech out in San Francisco here this morning. But today I wanted to speak to you in my role as vice chair for the Allotrope Foundation and to talk to you about some of the things that we've been doing, especially some of the new initiatives that Allotrope's had around standardizing data and making the pieces of the puzzle that we have to standardize your data more accessible and easier to use. And so to start with, I'll talk about, the laboratory data fads that we've had, right? We've seen many, right? Originally, these came from data silos, data warehouses, data lakes, data fabrics, data meshes. It seems like every few years, there's a new way for us to discuss, how we're going to organize our data. And, the data that we have here can consist in all these different pieces, but the data itself is still the data, right? And what we're really looking at is how do we manage that data, especially as we start to talk about things like machine learning or advanced analytics. How do we put all of that data together, no matter what system it's stored in or what the new sort of way to analyze and organize this data is this year or next year? The data itself is still really key. And this is something that I think came out from something called the Data-Centric Manifesto, which some of you may have seen pretty recently. Data really is what drives our organization. So Allotrope represents at its core a number of different pharmaceutical and chemical companies, right? And then also as part of our membership, we have folks that create instruments and create scientific software, and all of these different things run on data. And so data really is that key asset. Taking it beyond sort of where we are initially and moving that to the place where we can really function with that data, talking about things like, for instance, the FAIR principles that we'll mention in a second. What we're really looking at are a couple key pieces. We really want that data to be self-describing. We want it not to rely on any specific applications because applications come and go. We really want that data to be open and non-proprietary, and we want it to be something that all of us can share. And so I mentioned just a second ago, something that I'm sure you're all familiar with, the FAIR principles, right? The data should be findable, accessible, interoperable, and reusable. And I thought maybe this morning, what would be interesting for us to see, and this I'm told is completely anonymous, but it would be interesting to know with a poll here, when you look at the data across your organization, especially the data in your laboratories, what we've sort of found is that folks follow a progression here, that it's simple and easy to create the data in a way that makes it findable, and then we can layer in these other pieces on top. And if you'd be so kind, with the poll that's coming up here now, just to say, where do you think your organization is? just so that we can get sort of an interesting idea of a little bit of an interesting insight into sort of where you find the data to be within your own organization and your own company. So while we're doing that, I'll continue on a little bit and talk about these in a little bit more detail. I think what we find is that the FA part is easy, but the FAIR part can be somewhat difficult. And that's the challenge that I think Allotrope is really interested in helping solve for the community. Findable means that the data set can be found with the relevant metadata. So it has the metadata that can tag it. A lot of folks now have really, I think within the last 5 to 10 years, focused on this, getting their data out of individual applications and into places where that data then can be accessible. So we can access that data using different defined usages and different business rules. In here, right, we're really talking about making that data open and available, within your company, right? So that folks might be able to use it for a secondary use of your data. It might be able to look at things like, for instance, using machine learning or different algorithms to be able to find new insights in the data that you have within your organization. But where we find that it's really much more difficult is to look at how do you make that data interoperable, right? The data comes out in a number of different formats, in a number of different ways. And so being able to make that data all talk to each other can sometimes be very challenging. And ultimately, what we really want to do is we want to make this data reusable. A lot of companies spend a lot of time whenever you're creating this data to be able to have a lifetime of that data that's beyond just the single experiment. And so really making that data reusable is really important. And so I understand we have the results ready from the poll. Yes, and so here I can read them off. And thank you everyone for responding. So 27% said the data is findable. 41% said the data is findable and accessible, right? But if we look at the findable, accessible, interoperable, and then reusable, only 10% in total said that it was interoperable and reusable. And a quarter of you said that, not quite there yet, right? Starting that journey. And I think this is very much in line with what I expected coming in to the presentation today, and very much in line with our conversations that we've had at Allotrope with different folks. So what I really want to do is spend the next 10 minutes to talk to you about the data and really about where Allotrope comes in, and we've heard it mentioned in a few talks this morning. How do we make that data really interoperable, and how do we make it available for everyone? And that's really what Allotrope is here for, is how do we make this data accessible to all? And so we can think about it, an application-centric environment really, for the most of us, defines the data in the ecosystem. So we talk about things like the data-centric manifesto, but I think the reality is that where we're living right now is that we have a lot of different systems. We'll take instrument software as one, but it's not the only one, right? They create a number of different pieces of data in a number of different formats, and those formats are not open and they're not standardized. Now, within the field and within sort of our domains within the last 15 years, there have been a lot of different initiatives to go out and to create more open representations of that data, to open that data, but not necessarily to standardize it. So a lot of these different initiatives will occur within one particular domain. So for instance, there might be a open standard within mass spectrometry, but that's not compatible with the open standard that's coming out of the NMR space. And so what Allotrope really set out to do over the last several years is to see, can we make a interoperable system of these different domains that really is open and really is standardized? And so what is Allotrope Foundation? So Allotrope Foundation, if you're not aware, is a pre-competitive consortium of different biopharmaceutical, chemical, and life sciences companies that have banded together to think, how can we make this easier? How can we work together to establish these standards that we can all benefit from? And so the Allotrope Foundation is made up of different member companies, and then our extensive Allotrope partner network, which I really think is sort of the key to making this work. So we have a number of different folks. Many of the folks that you've seen talks from today, are also part of the Allotrope partner network that are working together, as our entire community to be able to get this done. And so how does this work? How do we create a model that isn't just one single company proposing it or one single academic lab, but really represents the community. And we do that through our modeling process. And so we do that by first identifying subject matter experts. So these come from our member companies, these come from all across our community that are experts in a particular domain, and they can identify the key data elements in that particular domain. And then they work with folks within our community that are semantic modeling experts. So this means that the folks that have the information about the particular domain don't need to know things about semantics. They don't need to know things about how all of that gets organized. We have specialists within our community that have stepped up that will work with folks to be able to do that, to be able to take the different key pieces of information and work them together into a model. And the reason why we want to do that is we want to make sure that that model is interoperable with the other models that we have within allotrope. And so we have a governance process that's established. We have the criteria laid out on our website that governs how we do make sure that this model is valid and it's interoperable. And most importantly, that it's interconnected with all of our existing allotrope data models. So we don't create a model, say, for liquid chromatography in a vacuum, and then create one for, let's say, Raman spectroscopy. You know, we don't create those separately and make sure and make sure that they don't talk to each other. We make sure that they reuse common pieces. So that way you can connect all of that data together. And ultimately, these data models then get released to the community. And what's really important too is that the data models themselves also don't exist in a vacuum. They exist alongside our allotrope foundation ontologies, which are a set of terms that are freely available. They're licensed under a Creative Commons license, and everyone can use them to standardize how we speak about our scientific data. And ultimately, then these feed into our tabular models, and our fully connected models are more semantic models. And over time, allotrope has, I think, really picked up within the last 2 years and has been creating a number of different models. The full list of models is on our website, which I'll share at the end of the talk. But right now we have 47 different models that have been proposed, that most of them are released. I think we have a few that are going to come out here now through the end of the year. But these cover a lot of very common techniques like liquid chromatography, gas chromatography. We have some coming out now on NMR and mass spectrometry too, in addition to all the other different techniques that are used in the analytical laboratory. So these data models are available and create sort of our framework of standardization. So we take these data models and we take the ontologies, and these standardized data structures then fit into sort of one of the last pieces of our puzzle, which is our allotrope data format file. So this format is a high performance binary data format. It's built off of the HDF5 standard. So it itself is built on standards that can contain all of the data in one self-contained package. And so this can be a file that sits on your file system. There's an API that we have that will let you access the data within this file. And we'll give you a number of different benefits, right? This now frees it, puts all that data into a single container that contains the context with it. It has instrument and vendor agnostic, right, based on our standard, and it implements a lot of these semantic capabilities that are really powerful for being able to connect your data together. Now, this is sort of, I think, if you've been involved with allotrope, this is sort of the standard product offering, right, that we've had, and it's very successful. A lot of companies have used this, but we've also been looking keenly to how do we create better adoption drivers? How do we get a way for folks to sort of get their on-ramp, to get their data out of that fair and accessible state into starting in that interoperable state? And while I think this is a great end goal for a lot of companies, you know, realistically, a lot of folks need sort of a way to be able to bridge to these sort of capabilities that might be more involved, things like knowledge graphs that are clearly very powerful, you know, but might not be something that can really be a great starter project to get standards involved in your organization. And so what we've really been looking at in allotrope over the last year, and what I'm excited to announce here, and we can show more at our Allotrope Connect conference coming up in a few months, are some of the pieces that we're adding in here to be able to accelerate adoption for folks and make it easier for folks to use. So if we take our ontologies and data models, right, we can create a number of different files here. And these are our semantic files that will then feed into things like, for instance, knowledge graphs. But what we understand is that for a lot of folks in a lot of uses, you know, the data models that we have there, which are great because they capture the key pieces of information for a particular domain, we want to have a simpler way to work with them, a simpler way to access them. If you talk to folks who are the data scientists in your companies, folks are working in languages like R and Python and using their work there. And most importantly, they're using very simple data representations. So JSON, which you may be familiar with, is a data representation that pretty much everyone is using. I can actually guarantee you when you logged onto Zoom this morning, the connection between the Zoom client and the Zoom servers were using JSON in the background. So this is something that's universally used. And the important part is that it's very simple for folks to be able to work with and to use. And so what we have here then is we have taken all of our data models and created a simple JSON representation of all of them. So now we can have files that have this JSON representation that are very easy to use, but represent the key pieces of data. And most importantly, are interoperable with our more semantic representations of the data. And so while you might be able to use the JSON files, for instance, to work directly in a downstream application or for your data science needs, these different types of data are completely interconvertible. So you can take the data that's in the JSON and move that back into the ADF files, the allotrope data format files, or even into just the semantic webs that we can use to build those knowledge graphs. And so here's just a very quick example of what that looks like. I mentioned JSON. We chose JSON because it's really the data format of choice today. We could have chosen things like XML, but JSON really, it's something that every single language out there, every single programming language, whether you're an enterprise programmer, you're a data scientist, you're a bench scientist, the languages and the tools that you're using can read and understand JSON. The JSON itself has structure, so we use something called a JSON schema to ensure that the data there is validated and correct, so that way we can ensure the data integrity. And as I mentioned, they're created from our data models, so they have the same representations of the data there. So you're not losing anything, right? It's just a different way to look at that data. And ultimately, it's still using our ontologies, right? So everything here is using ontologies and connecting it together using those common terms to be able to speak the same language. And of course here, there are some benefits to upgrading to the full allotrope data format files. For instance, you can get auditing and checksumming. All of those things are built in. So if that's important for your work, if you're doing, say, GXP work, right, you can do that. The allotrope data format in sort of the fuller data models do multi-technique support, so you can combine data from different places. And of course, they give you those full semantic representations that really give you that sort of higher level of reusability. However, we really think that these JSON models, these allotrope simple models, can provide a very easy on-ramp for folks to be able to start using standardized data within your company or as an output for your particular platform. And so how would you start this journey if you're interested in it? We find that a great place to start the journey is really to start with the ontologies, right? Everyone uses scientific terminology within their companies. And we can see it, I can say, speaking from my perspective at Genentech, even within different divisions within our internal company, we'll talk about terms and we'll use the same word, but mean different things, right? And this will happen if you're looking at sort of the bench, the analytical space versus the clinical space. It can happen in a number of different ways. And what we found, even within Genentech, is using the allotrope foundation ontologies is a great way to be able to start to standardize that, to make sure that we're talking about the same things. And especially when we have data from two different sources, that they're really representing the same thing, using the same terms. And as I mentioned, this is freely available, so you can go out and find it now. You can either download the ontologies from our website, or we find a lot of folks really like using BioPortal, right, which is part of the BioOntology suite. The allotrope foundation ontologies are loaded up there, along with thousands of other ontologies that can help to standardize your data. And that provides a really easy way for you to go in and search for things, to be able to access, to be able to look up what is the allotrope term for mass spectrometry, for instance. And then building on top of that, once the ontologies are available, we suggest looking at the simple models that we just discussed. This provides a nice, easy way that's really accessible for folks, working with the data, to be able to start to work with standardized data that's interoperable across different platforms, different vendors, and different techniques. Now, of course, you have to get the data into that format. And so Allotrope is a standards body. We're a standards company, if you will, right? We're a consortium we aren't a company that produces software, but there's a lot of vendors within our partner network that do produce the software to be able to take that data, either as a direct output of the software on a particular instrument or as a part of a third-party conversion service. And so one of the pieces that allotrope is starting to offer there is a term mapping service. So we can ensure that, if we look at a particular vendor A's particular instrument, they may decide, call these different terms, sort of different things. We can map those into the standard ontologies that we use in allotrope. So that way there's a standard mapping there that folks can use. And what's really nice about that is then that reduces making these converters into just a programming exercise. So no scientific knowledge is necessary. You can turn this over to a development team that may not be familiar with the science or the domain technique, give them this mapping term, and it's purely just a programming exercise at that point. So it makes making these converters really easy to do. And then of course from there, you can think about taking some of that data, and maybe you need some of the additional capabilities of the allotrope data models to really model out the interconnected web of how all of these different pieces of data connect. And then you can of course use that within our allotrope data format. And ultimately, what this enables you to do is to take that data and to standardize it in a way that it can be used across different platforms, different vendors' techniques, whether it's for downstream applications, things like artificial intelligence and machine learning, which of course we all know, there's a lot of work and a lot of excitement in that area right now, or sort of looking at these more advanced analytics approaches and looking at these overall knowledge graphs. And so, what we're really looking at here is a community that's really producing interoperable data. It really is a true community standard because folks from all across our different organizations, of which there's more than 60 different organizations that are involved in allotrope, and looking at that data together and really defining what is the true community standard, that we can all get behind and agree on. And as I mentioned before, we have 40 different techniques that are covered right now. And our ontologies really provide the common foundation there. And so I'm excited today really to tell you about the newest parts of what we've been working on with allotrope, and that's really the simple models, these JSON-based future-proofed approaches that will make it easier for folks to be able to work with the scientific data. And as I mentioned before, being JSON, this is simple to use. Every language, every system out there, can work with this data. And there's no API required. You don't need to load anything. You don't need to license anything, right? That data is there and it's available for you. And allotrope's data models and data formats, overall, if we include the simple models and the allotrope data models in their semantic representations, really let you link your data across different diverse techniques and create these HDF5 based standard binary data formats to also be able to do things like archive your data or transport your data around. So there's a lot of different ways that you can use the allotrope standards within your organization or within your software. And ultimately, these simple models can be interconverted to the more semantically rich data models, the full graph models here, and they can lead to a seamless upgrade path to be able to do that. And so ultimately, combining all of that with the terminology mapping really makes implementing these allotrope technologies a turnkey operation. And so this is something that we're really focused on in our product team. We have a couple employees that devote full time to helping our community adopt allotrope technologies, and they're really ready and eager to help, to show you how much of a turnkey operation this can really be now. And so ultimately, what's the end result? The end result that we believe is consistent connected data across your organization. And so with that, I'll wrap up and just mention that, our community is always growing. Our community is open. And so we'd invite you, to join us. You can learn more at our website at allotrope.org, or you can email us at more.info@allotrope.org. And with that, I'll wrap up and be happy to take any questions.
Great. Thank you so much, Corey. That was interesting. We, in fact, already have one question by Caspar. The question is, can you comment on the open non-proprietary format you highlighted in the beginning versus the license fees for instrument manufacturers that seem to be due for using the format?
Right. So I think the question is specifically around the allotrope data format. So I can't speak obviously to other formats or licensing. And you're right. So the current model for allotrope is that being a member, there are license fees, right? And that really helps to sustain our community. And there's a community membership there. I can tell you that right now within allotrope, we're re-examining that, right? Within the simple models and these more JSON-based models, what we really want to focus on is getting the standards out there. And while it's true, right, as I mentioned, we do have full-time employees that help to do things like the governance, right, and to run the community. And we want to make sure that we have a funding source that sustains the community. We're re-examining what that looks like. And so, I don't have an answer here. It's something that our board of directors is looking at. But to say that, we're looking at, are there ways, for instance, that we can make these other pieces freely available, right, so that we could really increase adoption. And I would encourage folks to keep your eyes on that, because I think we'll have some information on that very soon. The last piece I'll add there is that our ontologies, right, those are always freely available, right, and the specific license fee I think that's being mentioned is only for that ADF piece, right? The APIs there. And so, the other pieces that we talked about there, aren't covered by a license fee. And they're things that, as being part of the community, you would get access to.
Mm-hmm. Then we have another question from John Welsh. Are you saying that JSON does not do a good job representing versioning and auditing? So allotrope would be needed for a full compliant data model?
Right. So, I think there are ways, for instance, to be able to do versioning and auditing in JSON, right? What we're really focusing on here is the data representation, right? And so with the allotrope data format, the HDF5 based format, all of those things are there and are built in. Right. But, if I would say if there's a significant need within our community, to be able to look at these things within the allotrope simple models, then that's definitely something, we would look at.
Mm-hmm. Maybe another question from my side. How much do you think is the success of the allotrope data format dependent on the support of the instrument vendors?
Yeah, I think that's a great question. I think we've been fortunate to have very, very good interactions with a number of the major instrument vendors, right? And folks are really on board. A lot of the modeling, to be honest, that's being done in the community, is being done by partnerships with folks at sort of pharmaceutical companies that you might consider sort of the consumers of this data, and the producers, right, that are working, the major folks that are producing these different instrumentation. And so, I think it's a really fertile ground for being able to do that. I'd also say that we have a number of folks within our partner network and within our community that can sort of provide the service to connect the two, right? So there's always the ability, to be able to reach out to folks to do that. But I would say that I think, to be honest, right, I think that that's one of the key strengths of allotrope is that, the folks that are producing the data, producing the machines that produce the data, whether they're balances or their mass spectrometers, which is sort of my day job, or really any types of instrumentation, chromatographs, and the list goes on, having the folks that are producing the data, working with the data, and consuming the data from all across the community together to define those data models, I think is really a big strength of what we're doing.
Mm-hmm. Good. Do we have any other questions from the audience? If not, then thanks again very much, Corey. That was really interesting. And let's now go to the next presentation by Gerhard Nölken of the Pistoia Alliance. Let me first introduce Gerhard. Hi, I can already see him on the video here. Dr. Gerhard Nölken studied human medicine in Mainz in Germany. In 2001, he moved to Pfizer and worked as site head for discovery research informatics in Sandwich, UK. Since 2007, he was the global business IT lead for Pfizer Pharmaceutical Sciences. Gerhard is a co-founder of the Allotrope Foundation, from which we just heard, for analytical chemistry data. In 2016, Gerhard left Pfizer to set up his own consultancy, Data for Lab Limited. He now works for the Pistoia Alliance as the project manager for Lab of the Future. Yeah, let us welcome Gerhard, and we're looking forward to your talk.
And Annette, I'm co-presenting with Steve Emmerich.
Yeah, and Steve is the Director for Translational Informatics, Digital and Innovation at the US Pharmacopoeia in the US. Welcome, Steve, as well.
Perfect. Good afternoon. Can you hear me?
Yeah.
Perfect. So I tried to share my slides here. Nope, doesn't work. Maybe this way.
Yeah, we can see your screen now.
Perfect. Good. Welcome, everybody. Thanks for having me here today, Annette, and to all of the IQPC team. It's a pleasure to be here. And specifically, of course, it's a pleasure following Corey and his presentations, because now everybody in the audience is already an expert in allotrope data formats. And I can really focus on, let's say, how we in Pistoia Alliance are building on that great standard like allotrope data format. We started 3 years ago to build additional pieces for the ontology and our own data model to support HPLC. And this is what Steve and I will now be reporting about. So, Pistoia Alliance, another pre-competitive consortia, and I think presenting here together, we show that, let's say, pre-competitive consortia can closely work together. If I now get... Before I go into my talk, I would like to offer a polling question to the audience. We will be all talking in the presentation a lot about method descriptions. We will be specifically talking about analytical method description, but of course, wherever you work in the industry, let's say, just think of your method description. It could be chemical, it could be biological, whatever it is. We would be interested to hear your opinion if you are still managing this as a paper document. It would be the first version. Or a text file that you just store on your Office PC, or as a text file that is controlled in a corporate database, in an electronic lab notebook, or electronically with the instrument PC, which would mean, for example, a chromatographic data system or something similar. Or if it's not applicable for you.
All right, Gerhard, I'm going to pull the answers up now.
Mm-hmm. Perfect. So I think the winner is a corporate database. I think that's a great first step, having it in a central, secure place. But of course, what is probably not so supportive is having it as a text file. Even in an electronic lab notebook, you might not have, let's say, digital instructions that can go directly to the instrument. So what I think it's a great result, and let's say only 16% are, let's say, just having it locally as paper or on an Office PC. So it's very, very encouraging. What I would like now to show you is a way how we try to move from, let's say, the text-based analytical method description to a fully digitalized, machine-readable instruction set for HPLC. As an example, how, let's say, the allotrope data format can be used. Why are we doing this? Clearly, data reproducibility continues to be an important problem for life science. And some people state that half of the results are not reproducible and creating a huge cost item. In the pharmaceutical industry, it's specifically the challenge of interoperability. So you won't like to easily move your methods around. And let's say when you move them, you want them to be reproducible. Unfortunately, as we just saw in the poll, a lot of that information is still manually kept and managed. And if you have it electronically, it is stored in very proprietary software platforms. It's getting better on the result side, but remember, we are talking here specifically about the methods, the instructions you send, in our case, for example, to a chromatographic data system. So what we started planning about 3 years ago, and we are going to deliver the first proof of concept now in October, so just a few weeks away. We want to improve the automation piece as well as the interoperability for analytical methods, because only in the combination we hope to improve the quality, we optimize efficiency, and we reduce your cost basis. How are we going to do this? So first of all, the focus on transferring method from one place to the other. So in your department, freely sharing methods around, but not just in your company, ideally, of course, also on a business-to-business basis. For example, with a CRO that these days does most of the CROs that these days do most of the analytical work for pharma. By doing all this, we want to, of course, eliminate the need for manual data entry by, let's say, creating the shortcut between paper and the electronic platform. We need to enhance reproducibility, and that needs to include the full content of the experimentation. Only you have this combination of your data and the method parameter, you can do, let's say, the advanced analytical steps you need, for example, for an out-of-the-spec investigation or similar things. So let me illustrate that a bit more graphically for you. Today, we're in a situation where you manually have to interpret a paper-based document and, let's say, type this into your CDS system, for example. So without machine readability, you have little digital capability. You have no standard for doing this. So you have your paper documents, and let's say your results are often not as transparent as you would like to have it. So there are two ways you could go. You could increase the machine readability. That would at least increase your local scalability processes. But let's say the data elements most likely would still be unique to your vendor implementation. Or to look at the horizontal axis here, if you only do the standard, you will still have a lack on the digital capability, and the paper also will not go away. So, as I said before, we need to go both ways. Only by increasing the machine readability and relying on a good standard like allotrope, we will be able to have the automated data and parameter population. So we can send the parameters of a method to the CDS system, and it will be fully automatically executed. If you have all the data about the method as well as the results available, you can do a very different way of analytics. And this is, of course, specifically relevant if you are talking about the business-to-business environment. We certainly assume that, let's say, eliminating the interpretation steps from a paper-based description will increase reproducibility greatly. And you have the full context of experimental data available. This was really, everybody was focusing on just on the result data without the context of the experimental data. This is sometimes a really significant weakness. So let me briefly make a first summary here. We know that method recapitulation has been a problem for the business. The collaboration specifically between CROs and the pharma industry, but also with your collaborators, is delayed by those problems. We need the institutional knowledge. Remember that a method very often is developed in early stages, for example, in discovery, and then over the years of drug development, moves through research development to manufacturing. In each step, the analytical method you're using is changing, and you need to document that properly. With an electronic version of that method description, that will be a lot easier. And of course, with the platform, the allotrope data format, together with the ontology provides us, you have a digital standard you can build on. And now, after all this introduction, I finally show you how we did. Very easy. 3 years ago, we just assembled a group of chromatographers to knew a bit about their technique. We said, okay, there are certain pieces that theoretically make up an HPLC, a liquid chromatography instrument. You have a pump, you have a column, you have a detector, and maybe some software and electronics to analyze the results. Please tell us what are the common parameters and how do you name them? So you got, in the first iteration we did 3 years ago, we had about 27 parameters. The current version I'm going to show you, we have about 55. We got the names, and then we looked into the ontologies. What extra terms do we need? Which do we need to define and get them approved? And then, of course, we built a semantic data model. What you see here is a semantic data model for the first iteration, but we could prove in the very early POC that it works and represents the most important pieces of your analytical HPLC method. The next step was, of course, to make sure that the CDS vendors, the chromatographic data system vendors, the instrument vendors work with us, and we can build the adapters with them to the different instruments. What you're seeing here is, of course, an oversimplification of, for example, how a Waters Empower CDS system would be equipped with an adapter that allows you to download the method from the Waters instrument and upload it into the method DB, the method database, which is currently the central space. Of course, we could use any other semantically enabled database because there's a standard interface. And we can then use the parameters of that method to download it, for example, into Agilent OpenLab CDS and execute the method here. Within the method database, we have the search functionality, we have report functionality. So if you want to have a PDF or a paper copy of what you are doing is available. What are we talking about in terms of data? So as I said, in the first iteration, we had about 27. In the current iteration that goes live in October, we have about 55. We have a lot more parameters that allow you to link the sequence you're working with to your ELN and your LIMP system. We have a lot more data about the column, and Stephen will tell you what we try to do in the column area in a few minutes. And then finally, we have, let's say, full support for a whole sequence. This is, for me, the most important slide and my takeaway message for you. What we try to do here is we have your environment where you have your LIMS, your ELN system, maybe your workflow process tool up here. You send your samples, And we heard a lot of from Waters about what the sample prep is, of course, a challenge, and that needs to be included at some point. You send your samples or sample information to the instrument control system, so in the, typically a chromatographic data system. This chromatographic data system talks to the method database. You can up and download the method information. You can send it, that method information, to your CRO. You can send it to your lab next door and share it in the corporate database. By end of this year, we will also have an adaptive version that fully reports all your data and results. We are working on natural language processing support in order to make it easier, at least, to extract the important parameter out of text-based methods. We have gained some experience over the last 6 months on that. It is not as easy as we had hoped for. We need to improve it, but at least it is the first step, and we know what to deal with. Once we have all the data in this flow as well, why we're really doing it is we have the method parameters and the result data in one place. So that is really the time when we can use methods like advanced analytics, like artificial intelligence, to, for example, monitor the performance of all your columns, all your analytical assays. We have the chance to, let's say, use artificial intelligence to help with, for example, out-of-spec analysis to find the reason why your assay or your samples are not performing as you expected. So building this integrated picture for your data, irrespective of which analytical instrument vendor you are working with, having the flexibility to move that between different analytical vendors, moving it freely with partners outside your company, I think will change the way we are dealing with analytical methods. With that, I would like to hand over to my colleague, Steve. So before we do this, I give you the polling question too, and Steve will take over from here.
Thank you, Gerhard. Can you hear me?
Yep.
Okay. So I'm sharing the screen here. Oh, Gerhard, you might have to stop sharing before I.
Yeah, sorry.
It's okay.
I need to find the button. That's the problem.
Gerhard, I've done it for you.
Thank you.
And Steve, I will pull up the polling results now.
Right. So it looks like there's a mixed bag of responses there in the polling results. Okay, so can you see my slide? Is it showing?
Yeah, we can see that.
Great. Well, thank you, Gerhard, and thank you, everyone. I'm happy to be here today to talk a little bit about some of the things, to go deeper into some of the things that Gerhard was discussing related to leveraging standards that allotrope is creating to improve method interoperability, method transfer, reproducibility, which continues to be a challenge across the industry from everyone that we talk to. So I'm going to focus on the two areas that are evolving after the initial, after the methods database work started, which are the methods on demand, and then I'll talk a little bit about the chromatography columns data model working group. So first with methods on demand. Often with where we are in life sciences and pharma, we're starting with knowledge that's already been created by experts and exists in free text outside of any type of a data model that can inform that type of semantic interoperability and reproducibility that machines like, that we like to get out of scalable computer processes. So we're starting from these volumes of literature of analytical methods that have been together. And in my role at USP, if you log into the USPNF online, you'll see those in the monographs and the general chapters. They're written as voluminous scientific documents that describe in great detail how to comply with to ensure quality of medicine. So what we were interested in is how can we leverage some technologies like natural language processing to help with reproducible and scalable mapping of that knowledge to some of these ontologies like allotrope and others. So that's the problem that we were trying to solve for with the Methods on Demand project. So I'll just start with a little bit of an example here, and this is from my colleague Dana Vanderwall, who was the chair of the Allotrope Foundation board for 2 years. And he had put this together, and this is a nice example. It's an example of an analytical method. And if you're a trained analytical chemist, you could look at this free text and you'd be able to pull out information that you've been trained to know what's important. So you know what kind of instrumentation you're using, you see what kind of detector you're using. You know it's a C18 column from Waters. You know that it's the gradient, the flow rate of the column, maybe the temperature of the column. So you've been trained to look for certain information. But if you're a software program, you don't really know that. How does a computer know what's important enough to pick out? And the answer is that it doesn't really know unless there's some type of an underlying ontology or taxonomies to do that. So this is an example of mapping that free text to the domains in the AFO, material properties and results for the device that can help with that type of reproducibility that we're going for. It reminds me a lot of some of the things that I used to do before I came to USP in the clinical world, where you've got lots of free text notes and patient records and electronic health record systems. You might have things, there's a 70-year-old male with hypertension and depression, but all that knowledge is buried somewhere in the clinical notes, and you need some type of NLP algorithm to go over that and map it to the right diagnosis codes, map it to the right medications that you can support decisions. And a lot of the time we're doing these things so that we can scalably support decisions, whether it's in R&D or on the QA/QC side with regulatory filings. So I went off on a little bit of a tangent there, but this is an example of mapping that free text to ontologies like allotrope. And so we did some work in the Destroy Alliance with collecting monographs and methods from different contributors on the project, and then mapping those to AFO and the chemical methods ontology to support the review of those things and to really test if natural language processing could be used as a solution, where in theory someone from the industry could upload a knowledge set and come back with some type of tagged artifact. It can then be input for machine readability into a software platform. So what we found, this was the first time we'd ever done this. We scoped it pretty tightly around the chromatography data system parameters, a little bit of sample prep. And what we found is that there's some work to be done. The NLP, it found certain things, but it was also missing certain things. So we're kind of taking a pause here and looking at a second full iteration for improving the target model and selection extraction, and really the more content that we can use. Anybody that's done NLP knows that the more content you can feed into the system, the better you can train those algorithms on recognizing certain things against a foundational ontology or sets of ontologies. So that's what we've done with the methods on demand. And now I'm going to pivot to the chromatography columns data working group, and then we'll have a little bit of time for Q&A. But with chromatography columns, there's a similar need for interoperability of the metadata of those columns, such that when you scan a column from one vendor, it can be read by software from another vendor without undue effort or mapping on part of the end user. And so the hypothesis here is that standardizing that metadata can provide benefits for method development and execution, tracking the utilization of a column, which is, it's a problem, when is the lifespan of a column, and as well as inventory. And so the theory is that by standardizing the metadata, that could even feed in as input into models that are being developed that can improve the ability to select columns. So column selection is a challenge in the industry. Column similarity, that it's not a C18 column. What are the other ones that I can use? And so this work in terms of standardizing the metadata might be able to feed into that other work. And so we got started back in the spring. We stood up a project team. We identified our use cases, and we narrowed the scope there by really saying what we're doing here on this project is focusing on that metadata standardization. And to do that, we are soliciting contributions. We're going around and the contributors from Water and Agilent and others are giving us, what are all those fields that they enumerate in their columns, and then how can we map all those things to a standard. And then later this year, we want to send that out to the industry for review and comment, and then use that input in the next phase of the project. In addition, so I mentioned that we are one of the outputs of that metadata standardization could be used to improve our models. So one of our collaborators on the project is Dr. Dwight Stoll from Gustavus Adolphus College in Minnesota, who's been working on an HSM model to improve that column selectivity. And we're hoping that the work that we're doing at Pistoia with standardizing the metadata could feed into some of that. And so here's some of our next steps across all of these different projects. So, with all of these projects, we get started, and there's a core set of team members that participate. But then we have workshops like this. We have the Connect workshops where we want to hear from you. We want to broaden our participation and ensure that we've got all the use cases covered. So all of our contact information is down here at the bottom, and we'd be happy to hear from you if you have questions or comments or just want to learn a little bit more. And so with that, I will stop sharing. And I thank you for letting me present today.
Well, that was very interesting to hear from you too. We have one question, and I think the timing is perfect because we have time for one question. The question is by Dan Alexander. How do you manage to convert a method developed on one vendor's equipment to be run, respectively used on another vendor's equipment?
Let me make a start on this. By building the semantic data model based on a set of the key parameters for NH-build-C, we can map from one instrument to another. That will never be perfect and might, let's say, still require some human adjustment, but this is exactly what the semantic approach delivers us here. With this data model based on the allotrope ontology allows us that mapping from, let's say, a Waters instrument to an Agilent instrument. And if there are parameters that are not supported in the model, we can always include them as vendor-specific parameters in the underlying base method of the instrument. So we will be able to tell you a lot more about this in 6 months from now, how good it works. We know it works in principle, and we have done early tests with the 2 years ago, but now we are going to test whole sequences, and I'm sure we can report back to you in a lot better with a quantitative response in 6 months from now.
Wonderful. Thank you so much. Any other questions from the audience? If not, then thanks again, Gerhard and Steve. And it's time for today's last talk by Deepak Jose. He is head of business strategy and analytics at Mars Incorporated in the US. He leads multiple analytics and transformation programs for pet care, Mars Wrigley, food, and multi-sales segments, leading a global team of data scientists and business translators. Deepak focuses on areas including strategic revenue management, route to market optimization, portfolio simplification, marketing transformation, innovation, and e-commerce to drive profitable growth for Mars and its customers. He is an MBA from George Washington University School of Business and a mechanical engineer from NIT Calicut, India. Please join me in welcoming Deepak. It's a pleasure to have you here, and we are looking forward to your talk, Deepak.
Thank you very much. I really appreciate your welcome, and thank you for this opportunity to share our learnings at Mars. I'm going to share my screen. Let me know if you can see it before I start my talk.
Yeah, we can see it.
Excellent. So generally in this virtual world, I always start my presentation by saying, if we were in person, I would have started by giving all of you some M&Ms before we get into the details of how we do analytics at Mars. At Mars, we call ourselves Martians, and we are, as proud Martians, we believe the world we want tomorrow starts with how we do business today. And it has given a detailed introduction for me. In my current role, I lead several initiatives in the area of demand, including strategic revenue management, route to market, marketing, omnichannel analytics. And one of the biggest area that we are building our capability is around end-to-end analytics capability around innovation. I'll share some of the learnings that we had in the organization from a manufacturer standpoint. Again, from a smart R&D standpoint, I think some of you might already be doing it, and some of you might agree or disagree, but we definitely wanted to provide that perspective. But before I get into anything, I want to start by sharing a quick video about Mars, who we are, and what we stand for. Let me know if you can hear the video. Annette, can you hear the sound?
We can hear the sound, yeah.
Excellent. So let me play it once again. Thank you. I hope you enjoyed the video and it gave you a brief perspective about who we are at Mars. So I'll talk to you about leveraging data and analytics to drive innovation and growth, and what we are doing within the organization to break the silos and connect the dots from a data and analytics standpoint. As part of this session, I'll briefly talk to you about who we are as Mars Digital Transformation. What does advanced analytics mean for Mars? What is our data-driven innovation agenda? And some of the key enablers of our success, and we're happy to take any Q&A. Now, when the digital transformation leadership team started the journey in this area, we bonded analytics transformation to be a simple term which every associate can understand. And when we started the journey, we went with the theme of 100x speed. Speed is what we want to explain. Now, Mars as a company is more than 100 years old with more than 100,000 associates. So 100x, that's how we chose. And we have three key focus. We want to drive growth, improve our efficiency, and avoid risk using data and analytics. Now, at Mars, as I mentioned, this is one of the largest privately owned organizations in the world, with 454 sites with more than 2,500 hospitals, vet hospitals. Now, one thing which I learned for the first time when I learned about Mars was Mars is one of the largest employers of veterinarians in the world, which is part of the Mars pet care business, which is the largest part of our business as well. Mars Wrigley includes brands like M&M's, Snickers, and Twix, whereas the Mars Pet Care owns the brands like Royal Canin, Pedigree, Whiskas, Banfield Pet Hospital, VCA, etc. We do have some food brands like Uncle Ben's Rice, which is known as the Ben's Rice Original, Dolmio Pasta, etc. And Mars Edge is where we drive better lives through nutrition, the key four segments. So what is digital transformation for us at Mars? It is a very simple concept, and we use something called Mars Digital Engine to explain it. What is Mars Digital Engine? It is a simple four-step transformation process that we go through when we do any initiatives. First, find the right problem using user centricity and design thinking. You need to find the right problem before solving the problem right. That is the philosophy behind it. How can we use design thinking to frame and reframe the problem, which is the most important thing. Once you find the problem, then you can solve the problem using AI, machine learning, and the next generation technology in a reusable way that we are getting really, really good at this point of time. Once you find and once you solve, then you get into the automation phase. This is where you use capabilities like robotics process automation, the various solutions to free up the time and the resources. And that is the key 3 steps. And this is only going to work if and only if we deliver capabilities in an agile manner. In simple words, we want to think about progress over perfection. How can we have that mindset is very important to drive the experimentations of in the organization. Now, this Mars Digital Engine comes to action in every initiative that we are driving, which is a very important framework that we use. Now, what is advanced analytics? It is a very overused term within the industry, and it means different for different people. For us, when we started the journey, we want to leap forward Mars's capabilities, which was essentially focused originally, traditionally, from a descriptive and diagnostic area, which helps you understand what is happening in my business or why is it happening, to moving towards what is likely to happen and what are the actions should we take. As the complexity of the problems increase, what we have seen, the value generation potential has significantly high in this area. Now, when we started the journey, again, any organizations, any manufacturers can have three ways of doing data and analytics. One, from the foundation, it is a data-focused approach where you focus on automating the data. For a lack of a better term, you would, when you interact with the IT organization, they would give you a data warehouse, a dump of the data for the business to generate insights and take action. Then you have the insights-focused approach, which is a traditional consumer marketing insights team, a CMI team would do. Every month you would get continuous insights. I mean, those kind of analytics, they don't focus a lot on data automation, neither on enabling the decision. Now at Mars, we have consciously taken a choice to become very value focused or decision focused. You can think about from a data, our focus is more on decision. Now, the reason why we focused on this to drive analytics is because for us, when we went through our experience and when we were designing, we realized that analytics is not about just data to insights. More important thing is the insights to action. This is where we can drive the value creation within the organization. So that is one of the biggest focus. Now, when we started the journey, we wanted to have a value maximization mindset within the organization. Many of you might have seen this mindset, as we call as the inverted pyramid. In a traditional organization, if somebody asks, I mean, I've seen it, I've done it myself, we always focus on building a huge data foundation. Once you have the huge data foundation, we generate some knowledge and some insights based on it. When using these insights, we generate some action, which will create the value. And our provocation to Mars as a transformation team was, how can you bring value to the first? How can you think about how we can generate value? And thinking about those values and hypotheses, think about the actions that we can take. And from there, what are the insights needed to take those actions? And for those insights, what is the knowledge that we need? And for that, what is the data? And while we moved the focus from data to value, the one thing that we have seen is the quality of the questions that our team started asking significantly increased. Now, using data, if you ask the wrong question, numbers are not going to give you a better answer. It is the quality of the question that matters. And the value-focused approach helped us quite a bit. With this, let me deep dive a bit into the data-driven innovation agenda that we are building at Mars. Now, this is applicable for every segment at Mars, an overall framework, but I'll give you certain examples which has come to action for us. Now, our purpose was to enable all the activities related to innovation through advanced analytics, which included being strategic, moving the portfolio north to grow the category. The second one was to add the value faster. How can we innovate really, really fast? And the third aspect, how can we innovate in such a way that these capabilities go globally really fast? That was the key framework. And how did we make that happen? At an abstract level, what we have realized is that the real innovation happens at an intersection of data science and behavioral sciences. Data science is the algorithm that match or exceed human performance. And the behavioral sciences designing the user emotions to understand what is needed. And it happened through three different phases. You would use data and analytics to the foresight from the hidden patterns. Once you have the foresight, you build a deeper consumer understanding. And once you have the deeper consumer understanding and once you drive the innovation, how can you deconstruct the product success and failures? We went through these steps. Now, this was very important, and I want to share a quick story on how we designed the solutions related to data and analytics as we were building this capability. Now, what I am doing for the end-to-end innovation analytics could be applicable to various functions that you are part of. It can be within the manufacturing, R&D, even marketing, sales, every functions as well. Now, some of you might have heard the story of this bridge, which is about a Honduran bridge. It's called the Choluteca Bridge. If you have heard the story, apologies. This is, I read this with one of the innovators, Brett Munster, where he explains the need of building solutions. Now, in 1940s, Honduras, I mean, this story is about the Honduran bridge. In 1940s, the US government collaborated with the Honduran government to connect to vast majority of the land. They built a bridge to connect between these. Honduras, if you are familiar, it's prone to a lot of earthquakes, hurricanes, etc. So when this bridge was built, it was built to last with some of the strongest foundation. This bridge is called the Choluteca Bridge. So do you know what happened a few years later? So this was completed, and several years later, another hurricane hit the country. Now, because of the hurricane, the river changed its course because of several flooding. Now you have a bridge with no water under the bridge. Now, the reason I tell this story is thinking about how to build your solutions, specifically from a data and analytics standpoint, when you are building. The traditional way of thinking is build to last. And especially in this new normal, we need to build to adapt. Last year, for us at Mars, and for all of us across the world, the pandemic was one of these significant life-changing moments. And because of that, for us, a category like pet nutrition, it had its own tailwinds. For a category like chocolates, gum, it had its own headwinds as well. And because of the fact that we build a lot of our capabilities to adapt, we were able to take new and new data sources from the market to understand and add the feature engineering to do the predictions much better. And what does it mean from an implementation standpoint? When we wanted to build the right innovation solution, there are three words I want all of you guys to remember. If there is one thing which you want to take out of this presentation, this would be it. We wanted to build the solution in an interconnected way. We wanted to break the silos. If the true innovation has to happen within the organization, it needs to get connected to the supply chain, not only to the sales and category, but to the shopper behavior within the marketing. How can you build that innovation function with an interconnected way? The second, within each of the capabilities, how can you build these capabilities in a reusable way rather than a one-time solution? And finally, a white box. White box could be a technical term, but essentially it means the solutions that you built, wherever it is possible, the intellectual property should belong to you. And the minute you have that intellectual property, the data engineering layer, you are able to make changes. The modeling layer, you will be able to make changes, and on the visualization layer as well. And for us, this has been a key differentiator, which gave us a lot of advantage from that standpoint. And when we are building these capabilities, another focus area for us was we wanted to build this for all kinds of innovation. It was not only for a slight innovation which happened on the core capabilities. It was not for new segment entry or new business model from an incremental standpoint. we wanted to use this framework for breakthrough innovation as well, which is very important. And these capabilities we wanted to build across all stages of innovation as well, in identifying what does the customer need, which helps you understand what are the consumer attitudes, preferences, and what is the market white space opportunity. The second aspect is on the 4P, which talks about the concept and support. And finally, how to measure and improve all throughout the launch, which is about defining the goal and measuring success. Now, for us, subsequently, what we have done across what I just mentioned, in the beginning, I mentioned about the diagnostic, predictive, and prescriptive capabilities. We have mapped across 8 stages of innovation from a consumer needs standpoint, from a 4P strategy of innovation, and how to measure and improve the launch. We have identified capabilities. Now, it varies from diagnostic and prescriptive. Now, one of the specific areas where we have seen things working really, really well for us is around measuring the true incrementality. Now, from most of our, if you were to ask me, one is the most significant capability, which was the biggest game changer for innovation for us, is that incrementality. In many of the cases, we ended up investing on innovation with wrong assumptions on how it is going to cannibalize. What is the true incrementality of the innovation? So one of the capabilities that we build on measuring the incrementality and embedding within the existing SNOP process, which is not really, I mean, there were several capabilities that you have seen in the last page, but the true incrementality played a huge difference. And we are estimating several tens of millions of dollars because of this incrementality capability. We are able to add value to the organization. Being that said, what were some of the key enablers of our success? Now, before we call it success, I want to give you a quick view of what does it mean. When we took the help of an external management consulting firm, when we were starting the organization on where does our analytics capability land. In 2017, we were way behind. In 2018, 2019, we started making some significant progress. Now, because of COVID, we could not do the study in 2020 or 2021 yet, but we are in the area of making some significant inroads. Now, we just did not want to be the best analytics team within a consumer product company. Our vision and ambition is to become one of the best analytics companies in the world. The operating model helped us significantly to be successful in what we do. And as part of the operating model, there are 3 aspects which we have seen. I mentioned about the Mars digital engine, the 4 levers of finding, solving, automating, and delivering in an agile way, which is essentially on, and we had this mantra of business-led and digital enabled. The second aspect I mentioned on the agile delivery. This is very important for a 100-year-old organization like Mars. Now, people, there are within the digital and the technology organization, agile was quite familiar to everybody, but not for the entire organization. So teaching the fundamentals of agile, like what is a scrum master, how can you drive a sprint, how to do, those fundamental behavior shifts or the mindset shift was very important. So, and we keep on telling this story again and again. If you want to move from point A to point B, you don't need a Ferrari, you just need a skateboard. That is the progress over perfection mindset that we want to bring to the table. And finally, the iterative mindset. Now, in any capability within innovation or whatnot, we don't believe that we had the silver bullet. but we always were experimenting and we were going through this iterative learning process. And we had this mindset of building to think and launch to learn. And these experimentations, or at Mars as we call it, as a minimum viable product, was a game changer in the way we operated. Now, I want to share two themes before I close the presentation for today. This is one slide which is actively used within our innovation organization. Now, there is a rate of change and there is a time. We would always see the operating business moves in a logarithmic way, and the market technologies and the consumer preferences are changing in a exponential way. I want to quote Jack Welch here. If the rate of change of the outside exceeds the rate of change on the inside, the end is near. So the faster we can innovate, the speed, that is the biggest factor that we have identified that the data and analytics organization will be able to help drive the change. And how can we do it? It is through building the digital armor. We want every Martians to be the Iron Man and the Wonder Woman with the digital armors. And data and analytics is something that we want to provide to the entire organization so that they can move with speed. With this, I'm happy to take any questions and get your comments in the process. Again, I live with this belief that we have at Mars. The world we want tomorrow starts with how we do business today. Thanks.
Great. Thank you so much, Deepak. That was really inspiring. Are there any questions from the audience? If not, then I have a question. I really liked, among other parts of your presentation, the example of the Choluteca bridge. Have you, and I while you talked, I read a little bit about it on Wikipedia and found that they then rebuilt parts of the bridge so that it reaches over the water again and connects the two pieces of land. Have you experienced similar situations at Mars? So where you build a solution and then maybe during the process found it's really maybe not solving the pain point of the customer, or be it internal or external, completely, we're doing something new? And if yes, can you maybe speak a little bit to that?
Absolutely, absolutely. I think so the theme of build to adapt rather than build to last is very important for us. Some of the capabilities that we have built in the past, in some cases, we leveraged some external third-party vendors who gave us black box solutions. By black box solution, we give the input, they gave us the output, we don't know what is happening in between. Now, every time we wanted to make a change, either it was being really cost prohibitive. The second thing, we did not have the right level of accuracy. And the third aspect, we did not, there was no explainability as well. So moving away from a black box solution was very important. Now, how it helped us, again, we have, as part of our journey, in 2019, 2020, we were building several white box capabilities with adaptability in mind. Now, when the pandemic hit us, things were off the chart, right? Like our e-commerce business were accelerating. For a consumer like me who never used to spend a lot of time on e-commerce grocery purchase, things started moving towards Instacart. Same thing for a lot of the people. I'm sure that you would have used your e-commerce engine quite a bit. So having now, with the shift in the channel dynamics, those kind of data, the consumer preferences inputs, it started helping us driving the solution in the right way without any incremental cost. So that's one example where moving from a black box to a white box solution with the focus on building to adapt helped us significantly at Mars.
Mm-hmm. Wonderful. Thank you so much. So I guess it's time for my closing remarks already. This was day one of Smart Lab Exchange for R&D, and I hope you enjoyed it as much as I did. We had a lot of interesting insights and enjoyable, vivid discussions. First, Penny Smee, Simon Cook, and Martin Romacker taught us about the use of structured and unstructured data and how they attempt to unleash their data's full value by applying minimum viable architectures, standards, ontologies, text mining, and the like. We then heard from Waters about their OneLab product supporting lab automation and connectivity. Daniela Janssen, who is going to be the chair for tomorrow, led a panel about how to foster remote workforces with panelists Gitali Singh, Len Blackwell, Clark Leninger, and Zisis Koslakidis. You, the audience, then attended one-to-one business meetings and virtual roundtables, coming back to the main stage to listen to Mastrolab about simplifying automation processes. Basically, Gary Sharman showed us MNOVA and MGears software. Then Corey Bakalarski gave a valuable status update from the Allotrope Foundation. He was followed by Gerhard Nölken and Steve Emmerich, who gave us insights into their work at Pistoia Alliance, especially around the methods database. Last but not least, Deepak of Mars explained us how data and analytics drive growth at Mars.